Okay, this is OEH 5723, homework number 2, problem G. And so I'm going to try to mix between here showing this and showing the rest of it on the board. So the first part is, this question is all about, can you read the phase diagram? Do you understand what's going on? So we want to know, according to this phase diagram, what pressure in pascals is necessary to liquefy SO2 at 25 C. So we first have to determine in Kelvin what 25 C is. It's pretty straightforward. It should be 298. So here, considering how coarse this resolution is, I'm pretty much just going to try to draw my line right at the 300 and understand that the thickness of the pen is going to push me a little bit under, and I'll call that 298. Okay, so you can see I have an intersection of liquefaction, meaning going from vapor to liquid, right? So at this temperature, this is my intersection of the line going from vapor to liquid. So that's what I'm interested in. So I need to find what pressure that corresponds with. So it's important for you to be pretty precise here. So I'm going to take my pen, put it right in the middle as I can, and then I'm using my clear ruler, and I am trying to make my space on the top and bottom as equal as possible. Try not to bleed all over the paper because my pen likes to bleed. Okay. So that's my best guess. You know, this is graphical interpretation, so it's not going to be an exact science, but we want to be pretty precise because this is the log of the pressure. When you're talking about the log of something, a small decimal difference makes a big deal. So here I can tell that I'm not quite in the middle, but I don't know that I'd say that I'm more than 5.5, but I don't say I'm 5.7. So I'm going to call this 5.6. Alright. So now I'm going to transition up to the board and we'll see if we can't work this out. Got to zoom back out. Okay. So from the plot, we get that at 25 C, the pressure of the vapor is log 5.6, right? Or the log of the pressure of the vapor is 5.6. Sorry. So this is important for us to note that this is pressure in pascals. So it's the log of the pressure in pascals. So we take our anti-log, raise it 10 to the 5.6, and we should recognize that 5 means we're going to be in the 100,000s range, and then 0.6 we're going to be somewhere between 100,000 and a million, right? And since it's a log scale, it's pretty hard to predict what that value is going to be, but that's why we have handy dandy calculators. So 5.6 inverse log, this is 398,000. What? Pascals. Okay, so what does the question ask for? The question doesn't ask for what is the pressure in pascals. The question asks for, it does ask for the pressure in pascals. So there we go. That's it. What is the pressure in pascals necessary to liquefy? It's 398,000 pascals. Now, just as an aside, there's a little bit of extra information there that tells you that 1 atmosphere is equal to 101.3 kilopascals, or 101/300,000 pascals. So if I wanted to ask you how many atmospheres is this, it's roughly 4, right? But if we want to know exactly, 398 kPa, I just did the math in my head, divide by 1,000 to make it kilo, multiply by 1 atmosphere per 101.3 kPa, and that gives us atmospheres. So what is that? Divided by 101.3. Right, I didn't do my thousands. It's 3.93. So 3.9, roughly 4. So we have to put roughly 4 times the atmospheric pressure to get this SO2 to liquefy at this temperature. So if you were sloppy with your interpretation and you said, oh, that looks about like 5, or that looks about like 6, then you would have gotten a really different answer, and I'll show you real quick. So if this was 6, then this would be 1,000,000, right? So then that would make this 10,000 kPas. That's 1,000. 10,000. Wait a minute. I get myself confused. Here we are. Yeah. And then when we do this math, we would basically be at roughly 10 atmospheres. So if you spent this much energy pressurizing to this point, you'll use a whole lot of energy, but it would have phase transitioned after 4 atmospheres of pressure. Now you've got all this excess pressure, and you're just pressurizing the liquid that's already formed. But if you made the same sort of mistake, you took a rough measurement and you did it on the low side, you said, oh, that looks like about 5, then you would have gotten 100,000 pascals, which would have given you 100 kPa. Do the math, it comes out to roughly 1, but actually it comes out to something a little bit less than 1, because 100 divided by 101, so it's something at point, I don't know, we'll just do it, 100 divided by 101. So 0.987. So you would have actually been putting a vacuum on this. You would have said, oh, it spontaneously will condense, but it doesn't. So it's important for you to be as precise as you can. If you're sloppy with your temperature, then you're going to intersect the phase diagram at the wrong place. If you're sloppy with your lines dropping down from the intersection, from phase transition, down to your pressure, you're going to get something that doesn't look like a big difference, but because it's a log scale, the difference between 5 and 6 is a whole order of magnitude. It's the difference between 100,000 and 1,000,000. So the answer is 398 kPa, or 398,000 pascals. I'll find the button here in a second.